Okay, kids, here we go. Now we move to the next chapter. And if you've seen the previous chapters, previous podcasts, you may see some difference. I was wearing my headphone like this, and somebody said, "Hey, why don't you wear it like this so it cannot be seen?" Maybe you are not even watching me, you're just watching the slides. But you're hearing my voice. So anyways, here we are. We looked at changes having started mostly with the Industrial Revolution, and we talked about past climate changes, and obviously we can understand a lot about how climate changed even during the Holocene in the last 10,000 years, during which we went from being hunter-gatherers to agriculturalists and then the modern human beings living on science and technology. So some paleoclimate people, remember paleoclimate means past climate. Some paleoclimate people like Bill Ruddiman, I think, who is now at the University of Virginia in the US, argues that actually we were having big enough impact even before the Industrial Revolution, that we were doing large-scale agriculture and deforestation, and we were building cities, and population was growing. So maybe climate change started before the Industrial Revolution, and you can look at CO2 and so on, and temperatures up and down, and see that we did have some impacts, and there were big pandemics. You may have lived through the COVID-19 by now, and you experienced the pandemic maybe too early in your life. Somebody like me went through an entire lifetime without experiencing a pandemic till COVID came along. But there were other pandemics in the past, the Spanish flu of 1918 and some black plague and other plagues way back in the 16th century, and they killed so many people that agriculture literally stopped for a few years, and forests regrew, and they took down CO2 as well. So all these kinds of signals are there. So we had direct and indirect impacts on climate change along the way. Okay, so before that, during the last ice age and before, we were small in number and we were hunter-gatherers, and obviously we had some impact, but mostly we moved when there were climate changes. Humans, our ancestors, colonized the entire planet, and there is more and more evidence we keep finding, and that was in response to climate change. Now we are changing the climate and trying to do something about it, and there are people also moving now because of climate change. Brazil got flooded so badly this year in 2024 that there is large-scale displacement of people, and many of them said they may never go back. So we are still doing that. Now we come back to starting the measuring of CO2. We already mentioned Charles David Keeling a few times, and if you don't remember, scientist Charles David Keeling of the Scripps Institution of Oceanography, which is in La Jolla, California, a beautiful place on the west coast of the US, helped develop ways to take those CO2 measurements. In fact, it was his advisor, Roger Revelle, that we talked about before, who told him, he was the PhD advisor of Charles David Keeling, and he told the young man, you go there and start measuring CO2 because we are changing the CO2. And of course, Charles David Keeling, mostly known as Charles David Keeling. Okay, in US they have two names, and then they pick one of them for everyday use and so on and so forth. So he set up stations away from cities and factories to make sure he was measuring the free atmospheric carbon dioxide near the surface. He purposely didn't choose places near areas with higher than normal CO2 levels, because an industry may have locally high CO2 or a city may have higher emissions and so on and so forth. So that would throw off the findings. But one station he set up was in the Antarctic the other high on a volcano in Hawaii. That the Hawaiian time series, the Mauna Loa time series, became very famous and remains one of the most iconic figures in climate science that we will look at in a minute. So here is a schematic or a sketch of the Mauna Loa Observatory in Hawaii, which itself is a beautiful island to visit. If you're lucky, maybe you'll visit it. Built into the side of Mauna Loa volcano, this research center sits 11,135 feet, so more than 2 miles, and divided by 3 for meters if you want, and that's above the sea level. It is the longest running CO2 measurement station in the world. So we talked about using past proxies or paleo proxies like ice cores to estimate past CO2, but that's just an estimate. But here this is direct measurement. Findings are plotted on the Keeling curve, a graph that has become a symbol of human impact on climate change. As early as the 1970s, famous biogeochemists like Wally Broker, who was at the Columbia University in New York, said, look at the CO2 increasing, we are causing global warming. And he called the climate as a big dragon, and we said we are poking the dragon with a stick, and one of these days he's going to react violently. Daily measurements are posted on the observatory website. You can go and find it very easily. Check the bibliography in the back of the book to get the website link, but you are now smart enough to go and Google it and just say CO2 Keeling curve or CO2 Now, and there are many sites now doing this, NOAA and CO2now.org and so on and so forth. And there is an interesting story as well. Charles David Keeling's son, Ralph Keeling, also did a PhD from Columbia University. I think he worked with Wally Broker, and he started measuring oxygen. He continues to keep up the CO2 measurements started by his father. I think the father passed away maybe a couple of decades ago. The son, young bright man at the Scripps Institution of Oceanography, again as a faculty, measures oxygen. What do you see in oxygen? What do you expect to see? If we are burning fossil fuels at a very large scale, large quantities of it, with all the cars running, factories running, power generation, airplanes running around, everything we use, and this recording, everything is energy, there must be an impact on oxygen. We are burning so many fossil fuels that oxygen is in fact decreasing in the atmosphere, and Ralph Keeling monitors the oxygen as well. Do we have to worry about oxygen? Not really. There is enough oxygen in the atmosphere, so that's not an issue. But if we keep polluting, we cannot breathe. Our health gets really bad. Animals, dogs, everybody is suffering. So that's a problem of pollution, not so much loss of oxygen. Okay, so you can go find CO2 and oxygen and the isotopes of carbon we use to show that the increasing CO2 in the atmosphere, which is easily measured, as we will see in a minute, started by Charles Keeling, that is coming from fossil fuels, because the fossil fuels that were buried long time ago have certain fraction of certain isotope of carbon. If you want me to tell you quickly in a few words, I will say carbon has 6 protons and 6 neutrons, C12, and then there is C13 which has 7 neutrons, and C14 which has 8 neutrons. It's like carbon as long as it has 6 protons, and when photosynthesis happens, the ordinary carbon, the most abundant carbon, C12O2, is taken up by the plants more, because energetically, remember, plants have to use energy to do everything, to do photosynthesis. So they try to use as little energy as possible. So when they open the stomatas, it's easy to take up CO2 that is there most abundantly. But when CO2 decreases, more of the heavier CO2 like the C13O2, goes into photosynthesis. So depending on how much CO2 there is and C13O2 and C12CO2 there is in the fossil fuels, we can determine whether that came from photosynthesis or free atmosphere, because photosynthesis fractionates the CO2. Take some C12O2 and some C13O2. So if you don't understand, do not worry about it, but you will probably learn it again later. Okay, so leave this here and come back and continue this exciting discussion about how to measure CO2, who started measuring it when, and what it shows. That's the most exciting results. We'll look at the famous Keeling curve and we'll see what is happening to CO2. We already looked at it a little bit. We'll now look at it in this context again. So see you in the next podcast with the data collected by Charles Keeling, David Keeling, from the 1950s, and which continues now with many people measuring at many more places. The other thing you should remember that we discussed before, CO2 is inert and it gets to go around and gets mixed. So you measure it in one or two places and it gives you a nice idea of how much it is in the northern hemisphere or in the southern hemisphere, and so on and so forth. So you can measure it precisely and accurately. What does it mean? Accuracy means how much it is within, if I say 423 ppm today, how accurate is this measurement? It can be plus or minus 1 ppm. Precision means you can measure it 100 times and get the same value. So precisely and accurately we can measure CO2 in the atmosphere, and we can use carbon isotopes to say whether the increase is coming from fossil fuels or naturally occurring. This is very important. Okay, see you in the next podcast, kids.